Hello everyone. So far, I've introduced several hypothesis tests. They are all called parametric tests because in all of them, the dependent variables are measured on an interval or ratio scale and are assumed to follow a normal distribution. The normal distribution allows us to calculate probabilities, or the p-values, and estimate the likelihood of a statistic occurring by chance. In this video, I'm going to formally introduce the underlying assumptions of parametric tests. Different tests may require different assumptions, and I will use the independent samples t-test as an example. Independent samples t-tests have three underlying assumptions. First, normality. We can use a histogram or frequency polygon to examine whether the dependent variable approximates our normal distribution. In addition to visual examination, there are statistical tests of normality. For example, the Kolmogorov-Smirnov test or the Shapiro-Wilk test can be used to verify whether the distribution of a variable is approximately normal. Violations of the normality assumption may lead to inaccurate p-values. That being said, normality in t-tests is not always formally tested because significance testing relies on the sampling distribution. Based on the central limit theorem, we know that the sampling distribution will approximate a normal curve as long as the sample is sufficiently large. Greater than 30 is the rule of thumb, even if the variable is not normally distributed in the population. Second, independence. This assumption requires that subjects in the samples are independently and randomly selected so that the sample data are an accurate representation of the population. Independence is necessary for a more accurate estimate of the standard error. However, independent selection of samples is difficult to verify statistically. The best way to ensure independence is during sample selection, making sure that subjects have an equal probability of being chosen. Third, homogeneity variance, HOV. Independent samples t-tests require that the populations from which the samples are selected have equal variance. The HOV assumption is important because the population variance is estimated by pooling the two samples together. In fact, HOV is considered the most critical of the three assumptions because violations have the most severe consequences. Therefore, in the second part of this video, I'm going to demonstrate how to test for HOV. Here is an example. A researcher examined the effect of study strategies on test performance. One mixed gender group of 21 individuals was instructed to study for 5 hours the night before the exam. A second mixed gender group of 16 individuals were instructed to study for 1 hour per night across 5 nights. The individuals then took an exam scored from 0 to 100, with higher values indicating better performance. Assume that both groups were randomly selected. In the concentrated group, the mean exam score was 70 with a standard deviation of 10. In the spread out group, the mean was 80 with a standard deviation of 5. To test whether the two populations have equal variances, we start with the hypotheses as the first step. The null hypothesis is that the ratio of the two population variants is 1. Mathematically, it's expressed as sigma 1 squared over sigma 2 squared equals 1. The alternative hypothesis is that the ratio of the two population variances is different from 1. If we fail to reject the null hypothesis, we conclude that the populations have equal variances. In step 2, we choose the level of significance. The test of HOV is independent of the t-test, so it may have a different alpha level. For demonstration, I will use alpha equals 0.10. The sampling distribution of the ratio between two variances follows an F distribution. F distributions are a family of non-symmetrical distributions with values ranging from 0 to positive infinity. Each F distribution is determined by two degrees of freedom: the degrees freedom of the numerator, df1, and the degrees freedom of the denominator, df2. In our example, the degrees of freedom for the numerator is n1 minus 1 equals 21 minus 1, which is 20. The degrees freedom for the denominator is n2 minus 1 equals 16 minus 1, which is 15. The two degrees of freedom, along with alpha, are used to determine the critical value and the region of rejection. In our case, the F critical value is 1.924, given that df1 is 20, df2 is 15, and alpha is 0.10. Step 3 is the time to calculate the test statistic. The observed F value is the ratio of the two sample variances. In our example, the ratio of 10 squared to 5 squared is 100 over 25, which gives an observed F value 4. In step 4, we decide whether to reject the null hypothesis by comparing P with alpha or the observed F value with the critical F value. The probability of obtaining F equals 4 if the null hypothesis were true is P equals 0.004, which is less than 0.10. Therefore, we reject the null hypothesis. The comparison between the critical and the observed F values leads to the same decision. In the final step, we conclude that the underlying populations do not have equal variances. In other words, the equal variance assumption is not met. This result is somewhat unfortunate because for tests of HOV, researchers generally prefer to retain the null hypothesis, as it provides evidence that the assumption is satisfied. Failure to meet the homogeneity variance assumption means that additional considerations are necessary in hypothesis testing.